Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Still on the business of 2025 physics practical. This time around, we'll be moving to current electricity. Now, in this experiment, which is to represent the third question we are going to be having in this year's exam, what are the things we were told to provide? We need a potentiometer CB, usually 100 centimeters in length. Okay, we need a potentiometer, a rheostat, two cells, 1.5 volt each. That's two batteries, a voltmeter, 0 to 2 volts, an ammeter. You can see that on your screen, 0 to 1 ampere, a jockey. This is our jockey here. You can see that on your screen as well. A key, one standard resistor labeled RS, but the resistor is actually 1 ohms. Then connecting wires. Okay, looking at this, the question can go in so many ways. It could be a combination of the potential difference, that's talking about the voltage, and the ammeter reading the current, and at the same time it may just be about the current. But I think from what I am seeing, everything tilts towards having the current, majorly having actually the current. That is what it tilts towards. So what is the setup going to look like? What should the question look like? You can see that on your screen. You're going to okay, let's look at the board here. We're going to have a potentiometer. From one end of the potentiometer, we're going to use a wire to link that to the battery, then to the resistor. You can see we have a resistor labeled 1 ohms, labeled RX in this exam, RX. Okay, and after that we are going to have our ammeter to measure the current. Then we're going to have our key here. We're going to have our key. After the key is going to be connected to the jockey, with which we are going to look at various lengths on the potentiometer and be able to take our readings. Okay, and then we're going to answer associating questions. Okay, what is our question going to look like? As you can see on your screen, the question says, in the diagram below, represent electrical circuit in which CB is a potentiometer wire, E is an accumulator, that's talking about our battery, R is the standard resistor RX, A is an ammeter, key is the plug key, and J is the jockey. So that is the basic plan. That's we are to set up a circuit, close the key, and use the jockey to make contact with the potentiometer wire such that LCP equals to 20 centimeter. We're going to measure 20 centimeter. We're going to look for the 20 centimeter and use the jockey to touch that particular point. As you soon see in the experiment that we've performed, we found out that the more the length, the more the resistance, and the lesser the current that flows through the ammeter. I'll take that again, that we've seen that the more the length of the resistance wire, that's talking about the resistance per unit length, the more the resistance here, the lesser the current. You recall from Ohm's law that I equals to V over R. When this is an inverse relationship. When the resistance is more, then the current is going to be less. When the current is more, the resistance is going to be less. So when we perform this experiment, we found out that the more the length on the potentiometer, the lesser the current, because the more the length, the more the resistance. So in the question it says, such that L equals to CP equals to 20 centimeter, record the ammeter reading I, and we should calculate the reciprocal, that's inverse of the current. And we have to repeat this procedure for values of L, 30, 40, 50, 60, and 70 centimeter. Tabulate your readings. When we use the jockey to touch on the potentiometer at about a length of 20 centimeter according to the question, the ammeter reading is 0.30, and when we touch on the potentiometer at 30 centimeter, the current is going to reduce. The ammeter reading reduced to about 0.25, and on 40, on the potentiometer, when we touch, we had about 0.20, and touching at the 50 cm mark, we had 0.18 ampere. At the 60 cm mark, we had about 0.15 and 0.15, and at the 70 cm mark, when we use the jockey to touch on the potentiometer, we had about 0.12. So in the question, as you can see, it says we should look for the inverse of the current. Yes, inverse of I. That is going to be per ampere. So the inverse 1 over 0.3, if you compute, that will give us 3.333 to 3 decimal place. This will give us 4.000. This is going to give us 5.000 per ammeter, and that's the inverse. This means 1 over the current. Okay, 1 divided by 0.18 will give us 5.556, and 1 divided by 0.15, that will give us 6.667. 1 divided by 0.12, that will give us 8.333. Now, we could also be told to express the log of the inverse of the current. This will still be per ampere. So if we look for the logarithm of all of this, what we are going to have is 0.523, 0.602 if you compute, 0.699, 0.745, 0.824, 0.921. Look at it very well. When the length increases, the resistance is going to increase according to Ohm's law. And when the resistance increases, then it means the current is the ammeter reading is going to reduce correspondingly. This one just talks about expressing the current. That's the ammeter reading. That's just that according to that particular question. Then the next thing we were told to do is for us to tabulate our reading. We've done that. We were told to plot a graph. So the next thing on the question says that we should plot a graph of the inverse of I against L. So this is the inverse of I. This would be our vertical axis, and this would be our horizontal axis. This is what we have, and that's what we are going to now have to plot on the graph. The very first thing we do is to write our title. This is graph of the inverse of I per ampere against L on the potentiometer in centimeter. We've written that, and since the inverse of I is going to be on the vertical axis, you look at what we have. The least is 3 and 3.33, and then the highest point there is going to be 8.33. So we just want to draw our vertical axis first, making sure that our graph covers at least 60% of the entire space. So, and then on the horizontal axis, we want to first of all draw all of that and get done with it. So this is going to be our L in centimeters, and then this is going to be our inverse of the current in per ampere. Okay, now the next thing is for us to look at it. We on the for the inverse of the current 8.33. If this is 1 2 3 4 5 6 7 8, okay, it just goes that way. So this is going to be 1.000, 2.000, 3.000, 4.000, 5.000, 6.000, 7.000, 8.000. Okay, we've been able to pick our point, so that 8.33 is going to be somewhat just above here. Okay, then for the L is 20 to 70, so I could just go like 10, 20, 30, 40, 50, 60, 70. Okay, what this is looking like, if we are to write our scale for now, this from here to here is 2 centimeters. Inverse of I here is going to mean 2 centimeters to represent 1 unit. Okay, so I'm going to write 2 centimeters to represent, if you look at it, that is going to be 1.000 per ampere. Okay, that's what that will represent. And then for the L axis, which is in centimeter, that is going to mean 2 centimeters to represent 10 units, 2 centimeters to represent 10.0 centimeters. Okay, so that answers that about the scale. Okay, now let's just try to pick our point. When the inverse of the current is 3.33 at 20, 3.33, this is 3.1.2.3. So you're looking at somewhere around here, looking at somewhere around there, and 20. So our 20 is somewhere here. Okay, so this is the point, we've picked that. Okay, and then 4 and 30, 4 and 30, 30 and 4, that is very direct. And then the next one is 5 and 40, 5 and 40, very direct. And then the next one is 5.56 and 50, 5.5, 5.1.2.3.4.5 6, something around here. And then 50, if we trace that, and then 50 somewhere around here. Okay, and then 6.66 and 60, 6.1.2.3.4.5.6, somewhere around here. And 60, that's looking somewhat here. So we're beginning to pick our point that way. And then the last but not the least is 8.33, 8.33 and 70. This is 8.1.2.3. 8.33 is somewhere around here. So if we trace that, if you were using a paper graph, it would have been a lot easier, somewhere here. You understand? It's a lot more bigger than this, and you could actually get things a lot more. Next thing, according to the question, is that we have to get the slope of this graph. We have to get the slope of this graph. Okay, and possibly the intercept as well. Once you're able to pick 3 or 4 points, you'll be good to go. Okay, I'll go this way. You can see what our straight line looks like. just to get it so that we are able to get the intercept now. Okay, very good. This point here is our intercept. Looking at this point, this is looking 0.8, 0.800 per ampere. That is looking like our intercept. Okay, once we've gotten the we draw the straight line, the next thing we're able to get roughly about 3 points thereabout. Okay, the next thing for us is to try and get the slope. How do you get your slope? Your slope should be something like this. Okay, this will be our change in the inverse of the current, that is per ampere, and this here is going to be our change in this here is going to be our change in X, change in L, by the way, change in L in centimeters. So looking at this slope, if we are to calculate this slope now, this is looking, for this point, this is looking 3, and this point, if I trace this, if I trace this on the graph, this is looking this way. I can make use of extrapolated lines for this. Okay, this is looking 7.1, 7.25, 7.250. Okay, and this is looking 3. So my slope here, my slope, which is the change in the current divided by the change in L, is looking like 7.250 minus 3 divided by we are looking at 60. This is looking 60 if we trace that, and this here is looking, this is looking like 21. Yes, 21. This is looking 21. So 60 minus 21, 60 minus 21. So our slope is going to be 4.25 divided by 39. So that way our slope is 0.109 per ampere per centimeter. That is what our slope is going to represent, and that just about ends the graph. The next thing for us is to answer other questions that follows this particular experiment. So moving on, the next question, as you can see on your screen, says we should evaluate x over c. S in this case represent the slope and c represent the intercept. Our slope is 0.109 per ampere per centimeter. Our intercept c, that is where the straight line touches on the vertical axis, that is 0.8. Okay, when we compute this, okay, per ampere cancels per ampere. When we compute this, 0.109 divided by 0.8 will give us 0.136 per centimeter, and that answers that. So, okay, the next question states, what are the 2 precautions you have taken to ensure accurate results? You can things we can say things like I ensure tight connections in connecting, the wire to the ammeter, to the key, to the jockey. Ensure tight connections. Also, I noted and corrected 0 error on the ammeter. That just about answers that on the precaution. The next question is a calculation question. It says, if in this experiment the resistance per unit length of the wire CB is 20 ohms per meter and the EMF is 2 volts, the resistance is 2 ohms, and the length is 60 centimeter, Calculate the current in the circuit when the key is closed and the jockey is made to touch CB. It's just a question that goes in line with this experiment. You see in the question, it talks about, look at the question very well. It says resistance per unit length is 20 ohms per meter. So in this question, resistance per unit length is about 20 ohms per meter, okay? And the EMF here is about EMF is about 2 volts. What else were we given? We were told that the resistance R is 2 ohms, okay? That's external resistance, mind you. External resistance, you can see it in the question. External resistance is 2 ohms, and the length of the wire, is about 60 centimeter. Okay. Calculate the current when the key is closed. We were told to look for the current is the question, but if we are looking for current, we can just use our Ohm's law. According to our Ohm's law, current is going to be V over R. Now, in this case, this is what we actually want to do, use in calculating our current. But then, when you look at this, the resistance per unit length is 20 ohms per meter. We need to convert this particular length of the wire, which is 60 centimeter. We need to convert this to meter. This is going to be 0.6 meter, so that the resistance R of the wire, is going to be 20 ohms per meter times 0.6 meters. Meter, we cancel meter. 20 times 0.6, that is going to give us 12 ohms. The resistance of the wire plus the external resistance, the total resistance, our total here, is going to be 12 plus the external resistance 2. That makes it 14 ohms. Okay. Having done that, we're coming back here. Our I now is going to be voltage, that's the EMF, 2 divided by 14. 2 divided by 14, that is 1 over 7 ampere. And that's what our answer, 1 over 7 ampere. That is what our current is. Look at the question very well again, and it will make sense to you. I is V, that's the EMF, divided by the total resistance. Total resistance here is the resistance of the wire plus the external resistance, and that will give us our R total. So V over R, we are going to get our answer there. Okay. The next question talks about polarization and local action. It says, what is polarization and local action as applied to a simple cell? Now, polarization is a defect that occurs in simple electric cell due to accumulation of hydrogen gas around the positive electrode. And this effect of polarization can be minimized using a depolarizer such as manganese 4 oxide. What is local action? Local action of a battery is the internal loss of a battery due to local currents that flow between different parts of a plate, and this can be minimized using pure zinc. The answer there is on your screen. Now the next question says, explain why the EMF of a cell is usually greater than the terminal potential difference when the cell is used to supply current to an external resistor. Why is it that EMF is usually greater than the terminal potential difference? It is very simple. It is because of internal resistance of the cell. There is always this internal resistance resisting the flow of current. That is why the what is the voltage on the inside compared to the output is always greater. You see, EMF is greater than the terminal potential difference because of internal resistance. Then the next question says, state Ohm's law. That is what every one of us knows. The current, it states that the current through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance of the conductor. Very important. Your Ohm's law is very direct. It is I equals to V over R. What that means is that the current through a conductor is directly proportional to the voltage and it is inversely proportional to the resistance of the conductor. I equals to V over R. That is what your Ohm's law states. Then to the next question is, what are the factors that affect the resistance of a wire? You're looking at factors like temperature. The more the temperature, the more the resistance of the wire. Thickness of the wire is another one. If the wire is thick, the less the resistance, the more current will be able to flow. Thickness of the wire affects resistance. If the wire is thick, then the resistance is going to be what? Less. More space for flow of electron. That is what that means. Talking about factors affecting resistance of a wire, cross-sectional area is another one. The more the cross-sectional area, the lesser the resistance, and that just about answers that. And with that, we have come to the end of this lecture on WAEC 2025 Physics Practical Talking Current Electricity. From myself and the entire team, it's bye for now.